So as we've already heard, Ugo Fano has had an impact in many areas of physics, not only gas phase, but also solid state physics, and that his pioneering work, as well as the pioneering work of Fano and Cooper, have allowed tremendous advances in the fields of photoionization and photodetachment, which are the two areas that I've been working on. And these fields have actually benefited from a very, very strong collaborations between theorists and experimentalists, and that has allowed a growth in these two areas. So since the title of this session is Any Form of Resonances, I'm going to do just that. I'll be presenting some of our work on singly excited resonances, and I'll try to be brief there. We've also done some work on doubly excited resonances, and why not triply excited resonances, and we would love to do quadruply excited resonances, as we've heard this morning. However, we can't because safety regulations prevent them from looking at beryllium, so we will settle for shaped resonances. So all of the work that I would present is on inner shell photodetachment and photoionization experiments. And since it's inner shell, we need high energy photon. So therefore, it's going to have to be suitcase experiments going to accelerators. And since it's going to be suitcase experiment, might as well go to a very nice place like the Advanced Light Source, which is in the Bay Area. It allows us to escape the long winters of Michigan and also allow us to see very nice sunset close to the Golden Gate Bridge, but also give us very high intensity that allow us to measure very weak structure. It gives us resolution that allows us to separate between closely packed structures, and also give us tunability that allows us to scan over a broad photon energy range. So for the singly excited resonances, we've already seen from Hossein and other speakers how they actually occur. They basically occur because we have an interference between the direct photoionization and then the discrete excitation to discrete states. The two states decay to the same final ionic state, and therefore they would interfere and give us the characteristic Butler-Fano profile. Now, this experiment on Argon 3s NP autoionization was a warm-up for us because the ALS started in 94-95, we built a newly apparatus, and we wanted to do angle resolved measurements. So it's easy to start with an easier system. And although autoionization resonances have been measured before in other cases, like we've heard this morning, the only resonances that were seen were only the first few, and certainly they were not angle resolved. The measurements were done at 0 degrees with respect to the electric field axis. The experiment consisted of 2 time-of-flight spectrometer, one at 0 degree with respect to the electric field axis, and the other one at a magic angle. The measurements were done simultaneously so that we can get angle-resolved data. And so this is the measurement at 0 degree, and this is at the magic angle. And we were able to measure a few autoionizing resonances. The purpose of the work was to do a detailed analysis using a Fano model and extract the parameters from that. So this is what is shown in this view graph. We see here the first autoionizing resonances where there has been some data, but just for the first one. And along with this resonances are both a Fano fit, which is the green curve that allowed us to give the parameters, and also 2 calculations, one by Burke and Taylor, and another one by Tom Gorsica, who joined the physics department at about that time. So what we can see here is that there is a pretty good agreement between the theories and measurements. Tom's calculations were not shifted to fit the data because he worked very hard at trying to get the exact position, and he certainly succeeded for the higher autoionization resonances. And we also see a pretty good agreement for the high N autoionizing resonances. As I said, the measurements are angle resolved, so we can get the angular distribution parameter, and it is shown here. Again, for the first one, there were some previous data, and the calculations by Taylor, which actually were not tested in the case of the higher level, and also the calculation of Tom Gorsica. Again, we see a pretty good agreement for all of the lines. And as I said, the purpose of that work was mostly to be a warm-up experiment, and it was appropriate to show this work in this memorial since it allowed us to get the line width of the lines, the Fano parameter, and the correlation parameter, which, as we heard this morning from Joe Masek, was something that Fano contributed to us and the general community. As we can see from these window resonances, the correlation parameter tends to go close to 1. It's about 0.9 or so. I'm not going to bore you with all of the detail, and so I'm going to summarize it for you. The yellow highlighted data are the calculation by Tom Gorsica and our measurements. The measurements agreed, the absorption measurement as well as the photoelectron measurements that we have done. There is also quite good agreement with the configuration interaction of Burke and Taylor, the random phase approximation, and a poor agreement with the MCDF calculated by Tulki. In one of the theoretical papers, it was pointed out that the measurements weren't high resolved enough, or that it wasn't high resolution, because one could not discriminate between the random phase approximation with exchange and the R matrix calculation. And we felt that our measurements actually were able to show that point. And what we were able to see is that the Q value was better or more accurately determined with the random phase approximation with exchange, whereas in the case of the line width, the R matrix calculation did a better job. So in the case of the parameters for the beta parameter, as we know, the beta parameter is parameterized by X, Y, and Z. Again, that originated with the Fano formula and later by Kabachnik and Zazhina. And what here is shown, the calculation from Taylor, when he used just a single configuration, even the sign, the correct sign, was not obtained. However, configuration interaction was definitely needed, and he certainly did it in this work, as well as the R matrix calculation of Tom Gorsica agreed quite well with our measurements. So in this case, it's a happy story. Experiment agrees with measurements, but with calculations, but it doesn't always happen, as we'll see toward the end for other calculations. So after this warm-up experiment, we decided that we'd like to go to doubly excited resonances. And actually, we were intrigued by a paper published by Chen-Yan Liu and Tony Steres on some mysterious resonances that would appear in the partial cross-section, but would totally vanish in the total cross-section. In order to do that, therefore, one needs to measure the partial cross-sections. And so this is what is shown here. We decided to stay with the Argon 3s NP autoionizing resonances and separate the fine structure, the doublet P1/2 and the doublet P3/2. What is shown here is the two-dimensional map where the x-axis represents the binding energy of the electron, or the kinetic energy, and the y-axis represents the photon energy. So what we did is measure, using our time-of-flight spectra, several spectra, about a few thousands, and we measure one, we increment the photon energy by about 0.2 millieV, take another one, etc., and then we displace this two-dimensional image. What you could see here is that we're able to see, as we scan the photon energy, all of the autoionizing resonances that I talked about. We clearly see them here. We also see that the doublet P3/2 are more intense than the doublet P1/2, and so all of these window resonances that are here, and measured at the three different angles since we wanted to extract the angular distribution. So in order to get a scan, what we do is we take a cut along the y-axis at the three different angles, and there we should be able to see these window resonances for the total electron yield, and also for the partial cross-section for the sigma 3/2 and then for the sigma 1/2. So what we observe here is that these window resonances for the total cross-section and the partial cross-section mimic each other everywhere. And what were also observed before were two doubly excited resonances that are observed here and that we call DE3 and DE4 by Madden and Codling. But what we also can see here are these mysterious resonances that mirror each other's behavior. When one goes up, the other one goes down, and totally annihilate themselves or cancels out in the total cross-section. So these, as described in the paper by Chen-Yan Liu and Tony Steres, are mirroring type resonances. They're doubly excited resonances, and they arise in a very particular case, and this is when the correlation coefficient is actually tends to 0. So let's try and see if we can see them. Well, as I said, we do the measurement at different angles, so this shows it at 0 degrees and also, therefore, clearly seen in the angular distribution. But how can we interpret them? As I said, the two other doubly excited resonances, DE3 and DE4, were already observed and also were interpreted to being due to a 4p orbital that coupled with this ionic state. Okay? Now, since the two new doubly excited resonances that we observed were below, therefore the only possibility was to have a 4p orbital coupled to this quartet p states, giving rise to this possible LS configuration, which are triplet state. Since the ground state is a singlet, that means that it's LS forbidden. And so these doubly excited resonances are LS forbidden. They show relativistic effect. And it's in the case where rho square tends to 0. How do we see this? Where if the cross-section, defined also that way by Fano, is written in this way, rho squared also can be written as a ratio between sigma A over sigma A plus sigma B. The triplet state is very weak and would autoionize to triplet continua. And sigma A corresponds to this triplet state. Sigma B corresponds to the singlet state, which is more intense. Therefore, it's clear we're going to have a ratio of a very small number over a very big number tending to 0. And so these complete mirroring resonances are, as described in the paper, in the rapid communication of Steres and Liu, as being due to the case when rho square goes to 0. And this relativistic effect actually can also be seen in the case of the branching ratio, which, as was seen before, if it departs from 2, it clearly is a signature of relativistic effect. And if we do the branching ratio of our measurement, which is seen here and then zoomed here, it's 1.9. It's different from 2. And so this is a signature of some mixing between LS allowed and LS forbidden continua. So since we've been doing doubly excited states, and we've also looked at doubly and triply excited state in photoionization of lithium, and we've seen some of it or heard some of it in the talk of Turu this morning, we decided to try a little more challenging experimental problem and look at triply excited states in negative ions. So you'd say, why negative ions? Well, it's because they are strongly correlated targets, and actually they exist because of electron correlation. So we wanted to look at negative ions, do photodetachment of negative ions, and actually K-shell photodetachment of negative ions, ionize a 1s electron still with this photon source. Since we have a general audience, I thought that perhaps I should maybe briefly show the difference between a negative ion and a neutral. We're all familiar with the photoionization of neutral or positive ions because we have the long-range interaction that support an infinite number of states that converge to a Rydberg series at the ionization limit, as we just saw for the argon autoionizing resonances. We definitely saw a Rydberg series. And this is because of the long-range interaction. However, if you were to do a photodetachment of a negative ion, and I'm still in love with negative ions because my PhD thesis was in photodetachment, laser photodetachment of negative ions in a penning trap, and I always wanted to know what would happen if you were to excite inner shell. If you photodetach negative ions, you end up with a neutral, and therefore there is no long-range interaction. There's a short-range interaction, a shallow potential, which if zoomed here, and in some particular cases, that shallow potential or short-range interaction, if combined with the centrifugal potential, sometimes can give rise to a barrier that would trap an electron, giving rise to a shape resonance, as we will see it in a particular case, pretty soon. So, with that in mind, negative ions are different from positive ions. This is why we wanted to do photoionization of negative ions, because photoionization of positive ions have already been done actually by a variety of groups. And so we thought it'd be kind of interesting to look at this different beast. And our interest was even further more piqued when we saw the paper by the group of Charlene Zhu, Steve Manson, Vauquelin, and Alan Hibbert. They published a year ago a PRL where they had a photodetachment of negative ions, lithium minus and helium minus. And for the case of K-shell photodetachment of helium minus, the ground state is actually metastable. It's 1s, 2s, 2p quartet p. And if you do a K-shell photoionization, you excite 1s electron, you can end up with triply excited state. And so it's actually quite interesting to see the decay of this triply excited state to the core excited state of the neutral, helium neutral, which would subsequently decay to the Auger decay to the positive ion. So we start with a negative ion, and we do excitation. As I said, the shallow well may or may not support excited states. And so if there are they will decay to the neutral, or they could decay, autoionize to the core excited state of the helium atom, which would then Auger decay to the positive ion channel. Now, this is exactly the channel that we measure. We come with a VUV photon, we photodetach, so we have the neutral channel, but since we also can have a core excited state, we can also have a subsequent Auger decay, end up with a doubly detached target. And it is the positive channel that we measure right now. We do not look at the neutral channel for technical difficulties presently. So what do we see? I will try and see if the little movie I have would work. And what it would show would be the comparison between our measurements and 3 different calculations. 2 R matrix calculation, another one is a complex scale configuration interaction. So what we see here is our measurement that spans a broad photon energy range. This is the Zhu and al. R matrix calculation. Now it's the R matrix calculation by Zazzirini and Charlotte Forsch-Fischer. And now it's the complex scale configuration interaction by Jean Vicario and Eva Linthrop. And now we see all of them. So the first observation, or the first thing that we can't help ourselves noticing, is the big discrepancy in the intensity for the first structure, which is a threshold. So we have the first threshold, and then we have these excited states that would decay. So the first structure is the threshold, the detachment. And then here we have 3 structures. So we have a discrepancy here. And why don't we go and zoom in with higher resolution and look at the structure. In detail. So this is our measurement. Then we have the Zhu and al. Calculation. Then we have the Zazzirini and Charlotte Forsch-Fischer R matrix calculation. And then the complex scale configuration interaction by Jean Vicario and Eva Linthrop. And then all of them. The Zhu and al. Seems to agree better for the first structure, but not so much in the second one. Again, the 2 R matrix calculations are very similar. They treat the problem as photon plus target negative ion would give helium plus an electron, a 2-particle system. However, the complex scale configuration interaction deals with the photons plus a negative ion would give rise to 3 particles, helium plus electron, and then diagonalize the Hamiltonian completely. So this is the difference as far as an experimentalist can read and understand. And there is a discrepancy in the interpretation of the structure. The Zhu and al. Interpret this structure to be a threshold, this to be a triply excited resonance, and this is a mixture of the 2. But the 2 papers, the Charlotte Forsch-Fischer and the Jean Vicario, interpret the 3 structure to be due to triply excited resonances. And so right now there is a disagreement between them. There is a new paper by Linthrop and al. Trying to explain and defend their position. And I think that perhaps it would be followed up by the Zhu and al. Work. But what is interesting to note here is that, first of all, the photo detachment or K-shell photodetachment of a negative ion is very different from the one of a positive ion or a neutral, because the K-shell photodetachment would only, the K-shell photoionization of a neutral or positive ion would have a small monotonically decreasing cross-section with no structure. However, in the case of a negative ion, there is a lot of structure. The other thing that we want to notice is that it's only a 3-electron system, and it is not, doesn't seem to be an easy problem to tackle with present-day sophisticated calculation. So this is the point that I would like to bring. Now, the next type of resonance is a shape resonance, and we can see them in the context of K-shell photodetachment of lithium minus. And for the K-shell photodetachment of lithium minus, we do a similar process. We excite the negative ion to a variety of states if they exist, but we were actually very lucky because Zhu and al. Had a PRL out just before we did the experiment, and that helped us a lot to look for the structure, because these are very difficult experiments, actually. We have a signal-to-noise ratio to fight with and all sorts of technical things. But the process is excitation of the negative ion to possible state, they will decay to either the ground state of the neutral or the valence excited state, or to the core excited state of the neutral, and subsequently Auger decay to the positive ion channel, and this is the channel that we measure. So what do we see? Again, this is the same scheme. This is what we see. We see some sort of a threshold, then we see a clear shape resonance, and then another structure. Our measurements were corroborated by a simultaneous experiment by a competitive group in Denmark. And how do we understand the structure? Well, with the help of our theorist collaborator, Zhu, Manson, Hibbert, and Vauquelin, they predicted first a shape resonance, another shape resonance, this structure, and the two others. We definitely don't see these two structures. We clearly see the shape resonance, but with still the same discrepancy in intensity, and we clearly do not see this shape resonance. How are they explained? Well, they are explained by this excitation. In the case of the second one, since we see it, it'll be easier to look at. We have excitation to this state, autoionization to the core excited state, and then Auger decay to the positive ion channel, and we do see it. The case of this one, what was predicted was excitation to the 1s2s squared NP, then co-excitation of the state, and then Auger decay, but we do not see it. What Zhu and al did is recently to work harder at the experiment, at the calculation, since there were two experiments that agreed, so maybe there was something missing in their calculation. And what they did is included more configuration interaction in their calculation, used also polarization orbital that, according to my understanding, allows them to include the correlation that otherwise would be missing. And they ended up with this state being a little higher, which would make this state, the first one, the 2p, it's exaggerated here, lower. If it is lower, it's going to be a true Feshbach resonance. It will decay to the neutral channel, which, since we don't measure the neutral channel, we wouldn't see. And therefore, there would be here just a very small decay. The intensity isn't going to be in this channel, but more in the Feshbach resonance. And this is their new attempt, and as we can see, it's a better agreement, but my understanding is that they're also still working at it, and that there may be some PCI effect, post-collision interaction effect, because we have this loosely bound electron in the case of lithium minus or helium minus. It's about 0.5 eV, the binding energy, or actually in the language of negative ion, the electron affinity. It's about 0.5 eV. So we have this loosely bound electron there, and you come out and you photoionize or photodetach, so you have a photoelectron and an Auger electron. There are going to be some dynamics between them. Some energy is going to be stored in a certain way, and perhaps their calculation does not take into account this post-collision interaction. And I know that they're working on it right now. So, but it is a much better agreement now. And as, again, this is a 4-electron system, but it is still the present stage of many body calculation is not to the point of understanding these processes. So it's great. It keeps us in business, both the theorists and the experimentalists. So in summary, I'd like to say that study of many body processes remains central in many areas of physics. As we've heard, it impacts solid-state physics, and I also know cluster physics and chemistry. And technological improvement in computers and in light sources have allowed tremendous advances in inner shell photoionization, but also pioneering experiment in the case of inner shell photodetachment. But in the case of my experiments, I have reached the limit of light sources. And the one that I've talked to you about is the 3rd-generation light sources. Some of them are still being built, like in France. They're building one, and also in Europe, in UK, and other places. We've been lucky here in the US to have our 3rd-generation light source in 94, 95, but some of us are already reaching the limits of it. I'd like to do photoelectron spectroscopy, since I can do it for photoionization. The theories have calculated the branching ratio, they've calculated the partial cross-sections, and this is where we can actually see what is happening. And the apparatus is there, but the intensity is not there. As it is, to do these measurements, we have to fight signal to noise, etc. So we're ready for fourth generation light source, and it's good because they're actually in the process of being built. So we'll be playing pretty soon with this type of studies. And I'd like to end by thanking my experimental collaboration from my hometown, my students and postdocs under Western Michigan University, my collaborators at the Advanced Light Source, Denison University and UNR. And actually at Denison University, one of them is an old student of Dan Larson, with whom we both had our PhD studying negative ions, and UNR. And I also would like to thank my theoretical collaborators. Tom Gorsica has been a blessing for Western Michigan University because we've been able to work together in many problems. Basically, even before he arrived, he started doing calculation with us on these autoionizing resonances, and so we're very fortunate to have him with us. Chen-Yan Liu, with whom we did a collaborative experiment, Vo Kilen, Alan Hiberg, Charlene Zhu, Steve Manson, Tony Stairs, and Chris Green. I benefited greatly from very important discussions with both of them, and so I should not forget the funding, which presently is from the Department of Energy. And this is the picture of my group where we could see some of the students. Some graduated, Oleg Naindin graduated, and so did Wei Tai Cheng and Bath to their institution. Edwin Cook also has now a permanent position. Jordi Snell has a permanent position. John Bozek is our staff scientist at ALS and helps us a lot with the experiment. Burkhard Langer was my first postdoc, and this is now a student working with him. Sophie Canton is a student, a graduate student. She will finish pretty soon, and so will Marco Widenhoff. Thank you for your attention.
Questions for Nora?
The disagreements were in this threshold region. Is there any possibilities that it's an experimental problem as opposed to a theoretical problem if detecting low energy signals?
In the case,
that you're detecting.
right, you're saying in the case of the negative ion experiment?
Yeah.
Okay, so what would you say about this? Because these are two measurements. Here is the step, and this is the step. The measurements are lower resolution, okay? So you have two experiments carried out at two different continents by two different groups and two different instruments. And they see a step here just like we see. However, this is what the calculation predicts. So I think clearly, I'm sad to say that here it's clear. And of course, we see it in the next problem. For helium minus, there is only our experiment, so I cannot answer you the same way. But perhaps this leaves a good track record for. Yes.
So the higher lighting it looks like it's the same problem. They're not replicated by the experiment either.
These two, that's right. And these two are not replicated by the experiment, although this one we do see. And as we can see, they are as narrow. Actually, this one is narrower, and it's about the same intensity. But we measure this one and not these two. And so we think that perhaps it's the inadequacy of the calculation, which may not be taking into account sufficient, the state, these valence excited states, and whatever else that I'm not aware of. But Steve Manson is here, and so is Charlene Zhu, and so they could say what it is that they have not included. Yes?
I mean, the first one of those almost looks like a pseudo-resonance. It's a little broad.
Which one? This one?
The first one is not seen experimentally. No, further to the right. 63.7. The next one. That's it, that one.
Right.
That's really rather broad and would indicate that there must be something along the lines that you just said, that there might not be enough included, or it's not consistently handled, and then you can get this kind of
That's right.
stuff.
That's right. It may not be consistently handled. In the case of it, and it is puzzling, as we wrote in the paper. There are puzzling discrepancies. In this case, it's just a very good agreement. The shape, it's radio shape resonance. The intensity is missing here, as we can see, about half of it. just like for the first one. So even though here they get the position and they get the shape, the intensity is missing by a factor of 2. And it is true also when we go to the, in this case, right, the helium minus. I mean, the 3 different calculations miss out on this first intensity. So there is something big not included in the calculation. I don't know if this PCI is one thing, but since this room is full of theorists, here is a challenge to you. Go home and start working on it. Yes?
I'm just guessing, but I mean, on the experimental side, aren't these zero energy electrons?
That was my question.
Well, these are not electrons. I'm looking at the ions.
Ah.
Right. So we're measuring ions. As I said before, this is the channel that we're looking at. We're looking at the positive ions, right? We have the core excited state and then the Auger electron. And so we're looking at the positive ion right now. We're not looking at the electron. And I was saying, looking at the electron right now is not possible because there is not enough light intensity. What we can measure is the ions. We are going to be measuring electrons.
So the electron energy wouldn't affect the detection of
No,
ions?
no. Mm-mm. We will be measuring the very strong Feshbach resonance predicted in the case of helium minus. It's about 300 megabarn. It's huge. And there we will be able to measure that in the neutral channel. And also using photoelectron spectroscopy. But here it's the ions. So,
Jen?
As a theorist, could I say that I would have more faith in the experimental results? The code that those calculations are based on was written nearly 25 years ago. And I know roughly what processes were handled in that code. And it was certainly never written to handle this disparity of energy scales, which certainly comes into this inner shell photoionization of, in particular, negative ions. Where I think the interesting challenge is indeed the wide discrepancy in the energy scales possible between the electron affinity of the outermost electron and the binding energy of the K shell that you're really disturbing.
right.
So-
It's true. It's a challenging problem. I mean, both experimentally and theoretically. And perhaps what theorists are doing is using the code for the photoionization of ions or neutral, and it needs to be done from scratch. I have no idea.
Well, I think new things have to be probably put in from scratch. Yes.
And they've used a lot of configuration interaction and those polarization orbital to include this correlation, because negative ion are strongly correlated system. And this is why they are interesting. It's because we have these big discrepancies. But I don't know, Steve, did you want to say something?
Sure, why not? We think there are 2 reasons for the discrepancies. One of them is that the measurement, as was pointed out, is only one of the channels. So that means that that first big bump, if it's off by a few millivolts, you see, it can be predicted to be in the high enough energy to go to the positive ion, but if it's a few millivolts lower, it can't. And if it were a measurement of the total absorption, you see the neutral channel is left out. And so what we think is that partially some of the energies are wrong. As Ken very correctly pointed out, the R matrix code was never expected to get energies of thresholds or resonances right to the order of millivolts. There's a second problem. This is a more fundamental one, and Nora alluded to it, and that is the PCI effect. Basically, PCI effect, as everybody knows, is when you have a near-threshold photoelectron, and then an Auger electron, not and then, but also going to a state which then produces an Auger electron, there is interaction between them. And we see strong effects in the photoionization of neutrals when near inner shell thresholds. However, for a negative ion, it's even more fundamental because, look, a photoelectron leaving a negative ion should see a charge of 0.
Right.
But if an Auger electron overtakes it, then it sees a charge of 1. Percentage-wise, that's an infinite percentage change in charge. And this could dramatically affect the cross-section right at threshold, and that's exactly where the discrepancies are. Now, we haven't tested this, we're just thinking about this for the moment, but it may be that for inner shells, the whole Wigner way of looking at things for negative ion is really not completely correct, because in the calculation, in some sense, we're creating these we're treating these doubly excited states as if they were real bound states. So that's a possibility as well.
I think we better move on.
And with that, we should probably move on to the next talk. Thank you very much.